Good evening, folks, and welcome to the Advent of Code C++ live stream. My name is Craig, and tonight, as every night, we are going to be working through the Advent of Code puzzle drop in C++. Thank you all for watching, whether you're tuning into the live stream on Twitch or you are watching the stream replay later on YouTube. We're glad to have you here. If you're watching on Twitch, you can check the channel description. There you're going to find a link to the YouTube channel that has all the stream replays and a link to the GitHub repo where I upload all of the code that we write in these sessions. If, on the other hand, you're watching on YouTube, just check the video description right down there. You're going to find a link to that Twitch channel with the live streams and to that GitHub repo with all of the code. So, we are getting into the home stretch of Advent of Code. Just 5 days left, including tonight. We'll see, we're getting into a stage where there are some pretty challenging puzzles. Last night we did pretty well. Actually, I think last night we had our best performance so far this year in terms of speed. Yeah, 375 on part 2. Not too bad. Of course, the night before, day 19's puzzle, we spent a lot of time on. That took almost 3 hours to solve. Went off on a few garden paths on that one, but that was a fun one too. So we'll see where we get tonight. Maybe it's a real stumper. It might even be the case that I need to, step away from the stream without finishing the problem and have a little bit more of a think and come back to it. You never know, but we are in that stage where things can get pretty tricky now. So we have just about 2.5 minutes until tonight's puzzles unlock. I have already set up here, like I do pretty much every night, just the very basics of a program to start with. It's just a main function that returns 0, does nothing, but I do include the check library and the IO library that I've pre-written. Check gives us assertions, IO just gives us some pre-written functions that read in the text input that we get for our puzzles. And I've set up the build file here in the Bazel build system to tell it how to build that program. Just tell it what the source code is, what source code files to use, and what the dependencies are here, which are, again, those 2 libraries that we use pretty much every night. So we can see here we are descending further and further into the ocean in the search for the lost sleigh keys. Going deep into an ocean trench now. Be interesting to see what kind of puzzle we have tonight. We've had a few that are kind of like big on spatial reasoning. We had one that was like kind of a pathfinding challenge so far. There has not been so far there hasn't been anything that's been really tricky as far as like modular arithmetic, which has been that has been kind of a stumper in previous years. But you never know. We'll see what we get to. Usually for the Christmas puzzle itself, the day 25 puzzle, a lot of times that is a simpler one that you can get pretty quickly, and then the second star is kind of a freebie if you've done all the other stars so far. But you never know. Like a couple of years ago, it was a whole mini text adventure game built in the little int code computer that was used in the 2019 puzzles. So, you never know. We'll see. But yeah, we have just a few seconds left to go until day 21 puzzles unlock. And let's go! Dirac dice. Submarine computer challenges you to a game of Dirac dice. Game consists of a single die, 2 pods, and a game board with a circular track of 10 spaces marked 1 through 10 clockwise. Each player's starting space is chosen randomly. Okay, not that many places to start. Player 1 goes first. Players take turns moving. On each player's turn, the player rolls the die 3 times and adds up the results. Then the player moves the die that many times forward around the track. Okay? Each time a player moves, they increase their score by the value of the space their pawn stopped on. Player's score starts 0. So if the first player starts on space 7 and rolls 5, they would stop on space 2 and add 2 to their score. Game immediately ends as a win for any player whose score reaches at least 1,000. The first game is a practice game. The submarine opens a compartment labeled deterministic dice, and a 100-sided die falls out. The die always rolls 1 first, then 2, then 3, and so on up to 100, after which it starts over at 1 again. Play using the deterministic die. Okay. For example, given these starting positions, this is how it would go. After many turns, and then we finally get up to 1,000. Okay. All right, so part 1 seems pretty simple here. Let's go ahead and save our test input, day21.txt. Let's give that a look over here. Okay. And actually, I'm going to hard code these. But yeah, we'll say so this dice class, we're just going to keep an internal state here, and int next roll equals 1 to start, and then give it, it can just be default constructed. And then this roll will return, well, say, roll equal if incrementing next roll gives us greater than 100, then we reset it to 1. And we return the roll. Actually, let's do this. We'll do struct player state, and in there we will have int position, which is their position on the circular track, which goes 1 through 10. And their score, which is initially 0. So then we'll have this class game state, and we will have a vector of players. I'm not sure how this is going to expand in the next one, but I'm going to make this a little bit general, like making dice something that we can replace and substitute in, making the number of players something that we can change, just so that we can we have places to change things if the parameters of this change in part 2 of this challenge. So we'll have a vector of players, some number of players. We will have our dice. So we want to know the times that dice is rolled. So we'll just say int rolled for the dice. times rolled. We can return that rolled there. Okay. So we have our players, we have the dice, and so we'll have a constructor for game state where we just provide as an initializer list the initial positions of each of each player. So for each of those, we'll add a player state where the position is that position. Okay. So I'm going to do this take turn, which is which will do one turn for one player. So and this will return true if that player wins. So we will say spaces is equal to three rolls of the dice. Well, actually, so next position is going to be three rolls of the dice plus the player's current position modulo 10, because there are 10 spaces there. And then the player's score. Actually, I don't want those to be underscore because they are in a struct, so I'm going to go ahead and change that out here. But the player's score is then going to be increased by the value of the position they landed on, although we're counting these positions from 0. So we're going to say next position plus 1 is the point value they get from landing on that position, and then we return player.score greater than or equal to 1,000 for whether they won. So then we can just do int play until win, and you say do a big infinite loop on the outside, then for player state and player among the players on the inside, if take turn for that player results in them winning, then we are going to return, we need to multiply the losing player. Okay. So actually, okay, losing player. So instead of just iterating over player like this, I'll just say player IDX. So player index equals 0, player index less than 2, plus player index. So this isn't, fully generalized, but we're going to. So if the winner is 0, then the loser is 1. Otherwise, the winner must be 1 and the loser is 0. So we're going to take the score from the losing player times the number of times that the dice have been rolled and return that. So I may add parsing later before I upload this, but I'm just going to hard code the player positions. Now remember, they count from 0, so player 1's actual starting position player 1's starting position counting from 0 is 3. Player 2's starting position counting from 0 is 2. So we can just print out game.playUntilWin, and that should give us our result for part 1. And we actually don't need to add any extra libraries, amazingly. Let's go ahead and run that and see what it gives us. Okay. 983,070. Let's see if that is correct. Okay. That is not the right answer. Okay. Well, let's try 4 and 8, which is the answer, which is the sample data that they got, which of course adjusted to be 0 indexed is 3 and 7. Let's see what it gives us. Does not give us the correct answer. So well, let's see. Let's add a debug statement here. Let's see what info that gives us. Okay. Player 0, aka player 1, wins. The non-winning score is incorrect. The number of die rolls is correct, though. So we're scoring it wrong. So after each player moves, they increase their score by the value of the space their pawn stopped on. Huh. Is that somehow... You just parenthesize that wrong? No, that's not it. So we're rolling the dice the right number of times. We're getting the right number of iterations. And yet, we are not scoring it properly. This is going to get really spammy, but we'll say do that. We'll clear out the output so that when it, inevitably spams everything. So it goes 10, 3, 18, 4. Okay, so immediately we have gone off the rails. The weird thing is that we get to the right answer after what is seemingly the correct number of Oh, we're not modifying the player's position. That's why. We forgot to update the player position. And I'll bet you this gets us the right answer now. And I am sorry for... This is just a boneheaded mistake. I apologize. Yeah. That is going to give us the correct result once we plug in our actual input of 3, 2. Kind of amazing that it got us there after the same amount of time, though. Okay. 734, 820 is our answer. And we were slowed down massively. Okay, we got our gold star. Go on to part 2. Now it's time to play a real game. Second, okay. Dirac dice. As you experiment the die, you feel a strange. This is a quantum die. When you roll it, the universe splits into multiple copies, one copy for each possible outcome of the die. Okay, it could be 1, 2, or 3. Okay. We need to figure out how many universes we win in. Oh, yay. Well, this is one where we might have to figure out oh boy. Do some fun math on this. Well, so first things first, I'm going to go ahead and make a commit with the part 1 solution. And I'm going to go ahead and copy the part 1 solution to serve as the basis for our part 2 solution. Now we have really huge numbers here in the example for the number of universes that that we could wind up in. There are only 3 possible output results for each of these. I mean, obviously we can't simulate that many games that that are, it looks like, if I'm reading this correctly, it'd be hundreds of trillions of games to simulate. So that doesn't work. I mean, maybe there is a um, dynamic programming solution to this here because really, like, I mean, we can reverse. I mean, a given state of the game is determined by the positions and the scores for all the dice rolls. Um, hmm. You know, there might be something special about these numbers too. So I'm just going to use Python as a calculator here. I'm going to plug these in, and import math. What it? Oh, math.log. So I suspect. Okay. Well, no, it wasn't going to be an exact, power of 3 now that I realize it, because, not all games take the same amount of time. Um, well, for 3 rolls in a row, they can change the position of a player anywhere from 3 to 9, although the most likely change is 6. Like, there are more ways to get 6 than there are to get 3 or 9. So I think that what we need to do is we can count up the ways that it's possible for us to reach certain game states. So, whew, boy. Okay. Just thinking about how to structure this now. Obviously, we're not going to be using this particular dice class anymore. So I think that we're going to have we're going to want a set of we're going to want a map of player states to the number of possible ways to reach that player state, the number of universes, um, and then from a given player state, we can expand out, more universes from there where it's possible to reach. So we've got our game state. Excuse me. Um, We'll just add a method here. See, there aren't that many possible states here. Like, the number of states is, like, reasonably bounded, but the number of possible ways to get to a state is what's exploding. So that's the part that we need to, not compute every path through multiple universes that we actually need to count up. So that's just return score greater than or equal to 21. And obviously we stop on a win. And that'll just indicate who the next player is. So I'm going to add some equality operators and hash operators for these structs so that we can use them as keys in hash-based containers. So I'll say bool operator equals const player state other const turn position equals other dot position and score equals other dot score. And these should not be assignment operators, obviously. They should be equality operators. And then for hashing, to make it hashable using the abcel hash library, we just basically follow this recipe to plug it in to abcel hashing. So friend h abcel hash value hh const player state and p, and then we do return h combine, move the existing hash state h, include utility for that, and combine it with the position and the score there. Okay. And we'll do something similar for player state here. Sorry, for game state. Player 1 equals other dot player 1, not bracketed. Player 2 equals other dot player 2, and player 2 next equals other dot player 2 next. Okay. So Oh, and we need to implement the hash operator as well. So I'm going to just copy paste a little bit of that game state, call it G, and combine all the fields here. So G dot player 1, G dot player 2, G dot player 2 next. Okay. So initially we have our starting game state and one way to reach it. And now we need to figure out like what order to process this stuff in. Well, so the other thing that we can say is that we can say, given a certain thing, given a certain game state, we can multiply out, I guess. So I'm trying to figure out like what order we need to process the possible game states in, and whether we maybe start from like all the winning positions and backtrack, or we go forward and just um, cover the least likely things first. Hmm. Get rid of this other version of game state while we're thinking about it. Um, I'm going to put the test positions in here initially. So they were 3 and 7 when we zero base them again. Okay. So I'm just starting to sketch out this algorithm here, not necessarily knowing where I'm going to land, but I'm going to include flat hash map here. And so game state to int64t, which will be the count of universes that game state occurs in. And initially, going to have, just our initial game state and 1. And so if we start from that, and maybe we have a priority queue where actually, I think we can go through No, we can't increment everything because we would just recursively compute hundreds of trillions of times. So we can't just that would just be a path through simulating everything. So we need to I wonder, yeah, I'm kind of like beginning to sketch out like a dynamic programming approach here. But let's see. Okay. So, assuming that we have already figured out all the ways that it's possible to get to a particular game state and the number of universes that are possible there, then we can say we can look at the possible distribution of those 3 dice and what they would lead to in the next game. So the probability, okay, so thinking about the probability distribution for 3 dice, it's going to, well, there's going to be 1 way that it can be 3. There's going to be 3 ways that it can be 4. And, on the opposite end of the distribution, there's going to be 1 way that it can be 9, and 3 ways that it can be 8. Um, so ways that it can be 5, we can have 113, 131, or 311, or we can have 221, 212, or 122. So 6 for 5. And the mirror image on the other side of the distribution. And then 6 is the most likely outcome. That could be 222. It could be it could be 132, or it could be 123, 132, 321, 312. And I'm let you actually write these out now. Okay. Just to make sure that I'm getting all of these right. Dice can't possibly be more than 3, so it can be 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So those are 1, 2, 3, 4, 5, 6, 7. Only 7? Because I feel like those 2, 2, 2s. I mean, if we treat these as independent dice rolls, well, we've got 3 cubed possible outcomes, so that's 27 possible. Does that all add up to 27? Yes, it does. Okay. So, yep. So this is our probability distribution that we're working with. So we'll say and then, I'll just pass that as a reference, make this a little bit easier on myself, because I'm not that scared of mutable references anymore, since we allowed them in the style guide at work. Okay, so we've got our probability distribution, and for a given game state, then we'll say okay. And this player will fill out in a few different possible ways. So we'll say player so we know this probability distribution, but I'm thinking, like, are there ways that the same state can repeat in the game? And the answer is no, because scores always do increase. And so that might be the key to ordering this, because one player or the other is going to have their score increase on every turn. There's no way for the score to increase by 0. So there's no way for the initial state to be repeated. And if the given total of for a given total of 2 players score, there's no way that there's ever going to be a future state where it is equal or the same as that score. So I think that that is actually the way that we should approach ordering in this, is that we process lowest total score first. I'm reasonably confident of that. Yeah. So we'll say we'll add a method for that. Okay. So now honestly, we can make this expand itself. That might make the algorithm a little simpler, so I'm going to go ahead and do that. I'll move win up here like the other stuff, but yeah. And they'll just say so we'll return a map with all of the possible next universes in it. So this will be similar to what we are starting to look at, but we'll just say player 2 next, then so flip whose turn it is, and then we will go on to generate the different expanded universes. Now we'll just be using this little probability distribution that we calculated here, but we will yeah, maybe we won't. So, yeah. Actually, I wonder if I can just do. Yeah. Well, let me do it if I put in make pair. Yeah, okay. I can live with that. So there are 3 universes where the move is 1. Sorry, there's 1 universe where the move is 3. There's 3 universes where the move is 4. There are 6 universes where the move is 5. 7 universes where the move is 6. 6 universes where the move is 7. 3 universes where the move is 8. And 1 universe where the move is 9. And we'll go ahead and say we'll implement in this move in player state, and then well, actually, we can just, and we're going to be recalculating both the equals this one's position plus spaces modulo 10, and then next dot score is going to equal position plus 1, return next. Okay. So, player 2 is next. Next dot player 2 equals player 2 dot move universes dot first that is going to equal false, and then expanded dot, well, check expanded dot in place next move universes dot second dot second will give us whether the insert actually happened. Else, just going to flip this around and do it for player 1. And then we will return expanded universes. Okay. So I'm going to do a priority queue of game states to consider that is going to be ordered on their total score. So I'm just going to make a little comparator struct here. We're going to use that for the priority queue because remember, like priority queue is, the total score is always increasing. It can never go down. So as long as we process reachable universes in order of increasing total score, then we should never have to backtrack. Okay. So we've got our game to universes here. I'm just going to have a flat hash set of process because, you know, multiple states we're going to possibly put in with this expand universes here. So, or actually we'll just say enqueued. And then we'll, yeah, okay. And then we'll use priority. I'll have to include the queue header, but then we can get that. Include queue. And we'll do a priority queue of game states to look at. We can compare those with less total score. We need to tell it what kind of go ahead and just use a vector as your backing store, please. Okay. Do the main algorithm in main. So, okay. Well, toProcess is not empty. We'll have our game states here. we're going to this we don't need anymore. We implemented that elsewhere. So universe is in. Well, oh, we pop off the queue, so we'll just say top there, and then we'll pop the top. So we've got our number of universes in, the number of universes where we have reached this point, and then we will branch out further into all the other possible universes. So we will say for next state in current dot expand universes if enqueued dot emplace that next state, if that's the first time that we've seen that next state, then we're going to put it on the to process queue. But regardless of what we do, game 2 universes, we're going to for that next state, we're going to increase it by the number of ways to reach the current universe times the expansion factor, the sort of like fan out factor for different universes for the series of dice rolls for that next one. Or actually, so we'll do if enqueued, replace that second. If we stop on a win, so if not next state dot win, then we'll put it in there. Okay. So when this is done, game 2 universes should be a complete map of all the possible game states to the number of universes that they end in. And now we just need to count up the ones where there's a win and determine whose win it is. So okay. If game dot player 1 dot win player 1 wins plus equals universes if game dot player 2 dot win player 2 wins plus equals universes. And then we just return the max of those. Okay. So I think we have everything we need for a solution. I mean, we have hard-coded the sample data in there. We need to include flat hash map and flat hash set in our dependencies, and we actually need to tell Basil how to build this executable. So let's go ahead and do all that and see where we get. Yeah, we need flat hash set and flat hash map. And M comes before S, and I like to alphabetize these things. Okay. Just want to double check that in place logic here. Okay. I think, well, I mean, let's give it a go. Let's see, oh, okay. Fun stuff. A segmentation fault. So we accessed some invalid memory somewhere. Let's make a debug build and see, I mean, maybe we can get some more information by running under GDB. Okay. So hashing. Hashing. Wow. Okay, somewhere in expand universes, we got a problem with hashing. So it would be trying to put it into expanded here. I don't see why that's a problem. Unless it's a problem somewhere else here, like... Okay, expand universes is going crazy recursive though, so, and it shouldn't be doing that. Yeah. Oh, it's calling itself, so it's stack exhaustion. It should be returning expanded, not a call to expand universes, that's why. Boop. Okay. Okay. Well, that doesn't... 0 doesn't quite seem right now, does it? Make sure this is going as many times as we think it should be. Okay. That certainly went through plenty of times. Let's see what that looks like. Really think the numbers should kind of be going up generally. Um, hmm. Let's see here. It's the ordering of the cube. We want greater total score, not less total score. I always forget the order of the priority queue. Um, uh, now we should get somewhere. Dang. Okay. Maybe not. Um, well, it's still not monotonically increasing the way that we kind of think it ought to be. Um, they're visiting something with the same total score. Well, okay. There's different ways to get to the same total score. That's true. But we should definitely not be going up and down. Like, that is right out. So there's definitely something wrong if we can have, processing an item that's total score is 10 and then wind up with, next processing something that's total score is 9. Um, I mean, we start at 0, go 1, 2, 2, 3, and then we're back to 2 somehow. Um, I mean, that better be true in either case. Let's make sure. Let's see if that check fires. Okay. One of these went wrong. Oh, we're not copying this. Damn it, we just really make... I'm making some... not the smartest moves sometimes. But hey, you know, those check statements. Come back and help us. And that looks like the correct answer according to this. So we made some just, some real, you know, kind of embarrassing mistakes. Not always doing the math right, not always updating things correctly. But our algorithmic insight was correct the whole time. So let's go ahead and change that to our hard-coded input for this day. So player 1's initial position, initial 0 base position is 3, player 2's is 2. Rerun it. And that should be our answer. Let's go ahead and put that in the website. All right, we got it. Definitely slowed down. Okay, you know, it's not too bad. Like 1800 some for both parts. So I think the you know, we had the algorithm right basically. Just made some simple coding mistakes that slowed us down. But definitely it was right to you know, figure out, like, in an increasingly expanding universe, like, a key thing to realize is that total score always goes up. It never stays equal. It never goes down. So if you know that you found all the ways to reach a particular total score, then you can compute all of the possible outcomes of dice rolls from that total score without having to worry about backtracking and having to update it again. So that was pretty key. And then, you know, we figured out how to, you know, like, multiply out the probability distribution for all the different ways that you could roll 3 of these direct dice. What we were definitely slowed down by was just simple coding mistakes, like that less ordering of the priority queue instead of the greater ordering. That was wrong, obviously. And the score calculation. Oh, man, that was... just, you know, it was just a matter of, you know, like, forgetting. I mean, we did, you know, the plus equals, like, we were modifying the current one, but, you know, just need to remember that we were generating the next one, player state next, instead of the current one. So algorithmically, we had the right idea, I think, relatively quickly. Just slowed down by simple coding mistakes. But, you know, printing out what was going on helped us. Adding these checks to validate total score going up helped as well. And then that, you know, finally pointed us to, okay, calculating the score in player state move was incorrect, and that helped us find it. So you definitely got to see me exercise a few different, you know, quick and dirty debugging techniques today. I think this was definitely an interesting problem. Like, algorithmically, it was pretty cool, you know, being able to figure out how to keep on expanding the universes without having to trace every possible, you know, all hundreds of trillions of paths through. So, yeah, I mean, I had fun with this one. Like I said, you know, slowed down by some simple mistakes. But I hope you enjoyed this puzzle as well. So that's, I think, you know, we'll finish up the stream now. Once again, if you're watching the live stream on Twitch, just check out the channel profile. There you're going to find links to my YouTube channel with stream replays. and to the GitHub repo where I upload all the code that we write. If you're watching on YouTube, just check the video description right down there. You're going to find a link to the Twitch channel with the live streams, and once again to that GitHub repo that has all of our solutions. Thank you very much for watching, everybody. Thank you for bearing with me through debugging. I hope you had fun tonight, and I hope to see you again tomorrow. Bye-bye.